So I'm Diego BAEZ. I'm a solutions architect based out of New York. I focus primarily in financial services. Spent most of the last 22 years working in fintech. And now I work with a lot of clients to figure out what's the best way to apply these technologies to specifically financial services problems. This was working a minute ago. There we go. When everything fails, spacebar. I want to be talking about the framework that I kind of put around this problem. We're going to be talking about computing profiles and what are we trying to solve. We're going to be talking about ephemeral clusters, and I'll tell you what that is. I'm going to give you some practical recommendations based on usage. We'll go over a couple advanced topics, such as spot pricing, obfuscation, and other things that come into play when you're using ephemeral clusters. And finally, we'll do a recap. Originally, I had a demo that I was going to give you guys. But as you all know, the gods of demo are very fickle. And I didn't want to push them today, so I decided not to do the demo. But I do have a joke for you guys. You want to hear it? It's my favorite techie joke. Some of you might hear it because it's kind of old. But it's related to demos, by the way. So there is this developer that died. And he goes to the gates of heaven. And there is St. Peter's. He has this big ledger. Opens up the ledger in what this guy's name was. There are two columns. The left column has all the bad deeds he did. The right column has all the good deeds. And St. Peter's scratching his head and said, this is impossible. You know, you did good deeds, you did bad deeds, you're dead even. You did as many good deeds as you did bad deeds. I don't know what to do. So here's what I'm going to do. I'm going to give you two tokens, a blue one, so you can go up to heaven and check it out, and a red one that you can go down to hell and check it out. You're going to come back and tell me what you want to do. The guy said, sounds like a good idea. Takes the blue one, goes up to heaven, doors open. It's beautiful, peaceful. Everyone's in the clouds. Everybody seems eternally blissful. The guy says, this looks good. Goes down, puts the second token in, goes down to hell. Doors open, beautiful spring day, warm, cool, parties everywhere. People are having a great time, music, dancing. You know, it's like Animal House. It's just an amazing time. The guy said, this is exactly what I want to be at. This is what I want to be at. Goes back, tells St. Peter, you know, I decided to go to hell. This is my place. He says, okay, you sure? I say, yeah, that's what I want to do. Gets back in the elevator. Doors open, blazing hot. They start sticking forks in him, throw him in a pit. Stinks, and the guy's like, what happened? I was just here, and it was beautiful. And Lucifer turns to him and says, you must have seen the demo. Favorite techie joke, so let's get going here. So what is ephemeral? Basically, this is a dictionary definition of ephemeral. You know, it's fleeting, lasting. It lasts for a short period of time. For those of you that thought this was a snapshot presentation, it's not. Although that's the first famous implementation of what ephemeral is, ephemeral videos. You watch them and they disappear. What I'm going to be talking about is exactly the opposite of this. And you'll be surprised how many enterprises still have this problem today. I can tell you in 80% of my clients, this is still the case today. When they need to put a new cluster, they need to expand the cluster, it takes a long time to do that. You have to build a business case, translate it into technical issues, goes down to technology management, goes to infrastructure, goes to procurement, they have standards, goes back, it takes 6 to 9 months. And the bigger the organization, the worse this is. And it still happens today. I'm going to talk about the exact opposite of this. I think this is a broken system, and I'm going to show you guys some of the things that could alleviate this problem. And the best way to do this is think about computing almost like a utility. You know, when you want to drink water, you go to the tap, you open the tap. If you're a little bit thirsty, you put the glass, fills up, you close the tap, you drink it, you're done. You don't think about how the water got there. You know, what's the reservoir, what's the piping to get me there. None of those things. You simply use the water, open the tap, and off it goes. If we think about computing the same way, we shift our perception of this, and we go into on-demand computing power. We go into paying only for the resources that we use. And we shorten the distance between need and actual processing. Okay? Why is this interesting? Because this could be very cost-effective. You know, it saves me time, it saves me effort. I'm not wasting anything. I'm only utilizing exactly what I need. So it's very, very, very efficient, and it's very scalable for me as well. So in this idealized world, what do we need? We need three basic things to be able to make this a reality. We need first an endless supply of computing power. You know, if I'm only going to open the computing tab, I need to make sure that there's always going to be computing power available to me. Should always be on, it should always be ready for me on demand. And again, I should only pay for what I use. Second, this computing power is useless if I don't have a way of getting the benefit out of this. So I need to be able to say, I need computing power to run a numerically intensive task, and I should get that. Or I need power to be able to run a data intensive task, and I should be able to get that. So it's not only computing power, it's computer power that's tailor-made for what I'm trying to solve. And finally, we're going to need the infrastructure to be able to deploy onto these, manage, scale, and clean up after we finish. And I'll go back to those three themes later as well. But think of this as the basic building blocks to be able to get this implemented. Let's talk about computing profiles. If I look across my client base, there's typically three types of problems they're trying to solve. Either they have very light tasks. Think of it initially as web-based applications. They're typically stateless. They're typically short-lived. They don't tend to have, state before or state after. They're fleeting. It's like a firefly. That's why I put a firefly there. They kind of shine one day and they're gone immediately. Very fleeting. All the information that they need to be able to complete the task is typically involved in the request. So everything is in there. I get the request, it gets done. The second big category of problems that I see is what I call data-intensive problems. If I'm an institution that needs to go through all the tick data for a particular day, that's 33 million rows of data. I need to be able to run computations on this. I need to sift through a lot of data for this. And there are many, many problems, especially with the growth of data that we have currently, which fits this paradigm. I need to be able to sift through a lot of data very efficiently. And finally, there's compute-intensive tasks. I need to crunch a lot of numbers, use a lot of CPUs, do a lot of, computational analysis, and I need something that does that for me. And each one of these is a separate bucket. You cannot solve one with two with three. Typically, they need to be solved very specifically. For the initial set, since it was web-driven, there are actually some interesting solutions already out there. The first web-based services were specifically aimed at solving this problem. It's what I call FAS, function as a service. For you to be able to put the function there, wait for somebody to make a request, execute it, give me the result. I don't care about state, I don't care where it lives, I don't care who provisions the infrastructure, I just care that this gets done efficiently and quickly. They typically are short-lived, and what they call idempotent or impotent, which basically means that if you do the same task multiple times with the same data, the result will always be the same. Give me a web page. If you request a web page, you're always going to get the same web page, right? Most of the guys with cloud infrastructure already have a solution for that. AWS Lambda works really well. You have Google Cloud Functions, which is the next rev of the App Engine. You have Azure Functions. You have IBM OpenWhisk and Watson. Again, these are all aimed at solving the same problem. And since they're all trying to solve the problems of how do I provide you with compute power for very specific short amounts of time with stateless infrastructure, then they put restrictions around it, right? They have limits on size of the function. They have limits on memory, limits on disk, limits on how long they're going to be able to run, limits on how many are going to be running at the same time. Again, if you're trying to solve the problem of how do I get these short jobs to run efficiently, I want them to come in, get done, and go away. So this is aimed specifically for this. Any questions so far? Ask questions, guys. I like questions. For data-intensive applications, the cluster actually happens to be a really good solution. Why is that? When you have a lot of data, you need to be able to split it out and distribute it among multiple nodes. And a cluster does this really, really well. It allows you to split up the data, split it along as many nodes as you have. It allows you to have parallel access to this data, so you can sift to a lot of things at the same time. It gives you fault tolerance. It gives you failover. It gives you many things that you would want when you're doing an application that is very data intensive. Machine learning, web analysis, genetics. There's a number of applications that fit this paradigm. But again, I have a lot of data. I want to be able to get a lot of data. I want to sift to a lot of data at the same time. Compute intensive actually is very similar, except that in this case, the CPU is the bottleneck. But again, clusters are really, really good at handling very compute-intensive applications. They do parallelism really well. And when you have a lot of computations, one way to be able to get to those computations quickly is to split it into multiple parallel computing paths and have everything executing as concurrently as you can. Again, clusters work really well for this. There's also the concept of a storage-aware computing, which is something that I'll come back here a couple times. You can always configure in a cluster in a way to maximize the parallelism of the computing power. So if you know that typically the data that a job is going to be accessing is going to be across 20 different servers, you can take advantage of all the cores in those servers versus trying to localize that data in 3 servers, and therefore you can have contention. Again, a cluster gives you the ability to be able to design things in a way that lets you leverage computing power. And these problems have been solved traditionally with a multi-tenancy cluster, or what we call a general purpose cluster. This is probably what most of our clients have currently. They spend a lot of time sizing the cluster, installing the cluster, looking at the use cases, trying to figure out how much data they're going to require, mapping that to disk, trying to figure out how much computing power they're going to need, mapping that to CPUs, set up this cluster, put all the governance on top of it, so they could then take these clusters and start onboarding use cases. That means that you're going to have one big cluster serving many, many different jobs for many different applications inside an entity. But again, it's master of none, slave of many here. So you have these general purpose clusters which work well, but always have the challenge that there's a balancing act. Multi-tenancy is a double-edged sword. It's efficient because you leverage in the same infrastructure. You're lowering costs because you're sharing infrastructure amongst multiple applications. But also, it has a high overhead. Job isolation is not complete. You can assign queues, you can assign resources, you can assign memory, CPU, but it's never fully isolated. They're still sharing the same resources. You need to pre-provision capacity. It's very difficult to say my cluster is this now, and I need to double the size of the cluster. And if you're going to do maintenance or reconfiguration of the cluster, everyone will get impacted. Questions? All good? Am I boring you guys, putting you to sleep? Couple more issues with multi-tenancy. And again, these are things that you have to take into consideration whenever you're designing a cluster that's going to have multiple uses. First one is called affinity, which is basically there's a profile per type of application, which is a profile that tends to favor one layout versus the other one. So if I have an application that tends to spread among 10 different servers and another one that tends to do one server, I have to balance those things. I need to figure out who am I going to optimize this for. So you have different profiles of clusters, and you have this affinity towards one type of application versus the other one. Second one is performance isolation, which I mentioned to you guys already, which is basically you need to be able to maintain SLS. Even if you have jobs that tend to start churning CPU cycles, you need to make sure that everyone in the cluster is going to maintain their SLS, and they have the performance isolation. 4 is quality of service differentiation. I need to be able to say, if I have a guy doing risk modeling, he needs to have priority versus a guy who's just doing, fishing, doing clustering in particular data. So I need to be able to determine this, and again, it's one of the challenges that you need to take into consideration whenever you have a multi-tenancy cluster. And finally, customization. It's hard to customize specific clusters for different things because, again, everyone is sharing different infrastructure. And here's where the ephemeral cluster comes in. The ephemeral cluster is a cluster that launches, processes a set of data, and terminates. This is not just another tenant in a multi-tenant cluster. This is a full-fledged, full cluster with everything that a cluster has. So it has resource management, it has utilization, it has all the packages that you want to put in there. It's a full cluster that launches and does something for you, what I call a unit of work. To be able to do this, it needs processing power available on demand. And I need to be able to say, launch a cluster that is going to be really good at numerical analysis. Or launch a cluster that's going to be really good at managing a lot of data. Or launch a cluster, I have a research group that wants to try something different, launch a cluster that has this particular profile. I need to be able to specify what I want when I launch these clusters. 0 initial state, process and forget, and 0 end state. So nothing happens before. Cluster gets instantiated. That's what it has to do. It dies. It gets destroyed. And can also be long running. So it doesn't matter to me that it's up for 5 minutes or it's up for 5 hours or for 5 days. It's going to be there for as long as I need this cluster to be up. But it's my cluster and it's dedicated to what I want that cluster to do. A couple more things. If you have a single purpose ephemeral cluster, then you don't have to worry about affinity. I built this specifically to do what I wanted it to do. So it's 100% affinity to my particular job. It has a dedicated quality of service. So each unit is basically has a concurrency of 1, which is my unit of work. It's not contending with anything else. It's always focusing in my particular task. It has performance isolation because it's only doing my job. No contention issues. You can run multiple clusters in parallel, which itself could be a benefit or a challenge. I can have a very clear audit trail. Everything that happens in this cluster for the life of this cluster is only focused in my particular job. Can't get any clearer and clean cut as this. I always can go back and say, okay, what happened this particular cluster for this particular job? Very clear, isolated, unique audit trail. And it can be customized. What are some of the issues? I have to manage multiple clusters at the same time. I don't have an easy way to be able to have actions that are going to affect every single cluster. Because keep in mind, every cluster is an independent cluster. And you need to be able to monitor that properly. Does this make sense? Questions? You guys are very quiet. Go ahead.
Do you have recommendations for how to launch an ephemeral cluster?
Yes, it's coming. Good question. Go ahead.
So on your clear audit trail, how are you collecting the audits from multiple ephemeral clusters to deal with like a single pane of glass to view all that?
I'll go into that. That's a great question, by the way. There needs to be something that is going to be unified, all this cluster, both from a management, from a launching, from a cleanup, and from a storage perspective. And I'll go into some of those options as well. Good question. Go ahead.
Is there any way we can store the structure of a cluster, or is it like every time I need to define it?
Yes, you guys are asking excellent questions. That's coming. You guys are asking really good questions. Okay, so what do we need? We already spoke about on-demand elastic computing. Second, exactly what you just asked. We need a way of storing recipes. I need to be able of storing, this is my recipe for an analytical cluster. This is my recipe for a data-intensive cluster. This is my recipe for a light testing cluster. I need to be able to make any number of recipes and store them, absolutely. And finally, you need the operational infrastructure to launch, adjust, scale, and clean up, which is some of the questions that were coming up here as well. This is another thing that I put in here because it's very important in the spirit of what we're trying to do here, which is basically you need to have an infrastructure that is cloud vendor independent. Why is that? Because if what happens with Amazon a couple months ago that went down happens again, and if I have the ability to deploy the same clusters in Google Cloud or Microsoft, I'm way ahead of the game. So I need to have a single way of interacting with multiple cloud providers to be able to launch my clusters. I shouldn't care whether it deploys into AWS, Amazon, AWS, Google, Microsoft, IBM, OpenStack, or on-prem. It should be absolutely transparent to me. I need to be able to deploy the cluster the way I want it, anywhere, without having to know the specifics or the mechanism in which it gets done. And we'll go into that in a minute. So the on-demand elastic computing environment, that's easy. That's the cloud. The cloud has, in effect, become a utility for computing power. That's what it is. It's generic computing power that I should have access to for as much as I want, and I should only pay for what I use. So we have that check marked. We have the environment, we have the mechanism to have quote-unquote limitless computing power. Nothing is infinite, but it's pretty close to it, Okay? The recipes. Without this wouldn't work. You need to have a way of capturing clusters and what they mean and how they can be configured and be able to duplicate that. Fortunately, we have Unbearable blueprints. Very straightforward. You can stand up a cluster, you can tweak it the way you want, you can go save blueprint, you have your blueprint. You can then feed that back in, and you can instantiate a cluster exactly like the one you had. Okay, I'll try to move quickly then. You can instantiate a cluster just like this one as many times as you want. That is a tremendously powerful model. You can have as many recipes as you want. You can tweak, you can come up with new recipes, save them as blueprints, off you go. You have your recipe for instantiating that cluster. Finally, we have CloudBreak, which is your mechanism to transparently deploy to any of these cloud providers. The mechanism is the same. The functions are the same. You don't have to know the specifics of AWS or Google Cloud or Microsoft or any of those things. Basically, you deploy clusters, saying I want to deploy a Google cluster, I want to deploy an AWS cluster. That allows you to deploy, create, change the parameters, add elasticity to it, grow them, shrink them, and destroy them. That's the glue that allows you to do that. Okay. Quick thing, how would you do this? Basically, specify a cluster type, which is a blueprint. Provision and launch a cluster, which is, I'll walk through the steps here in CloudBreak. You pick cloud provider, you click the type of cluster, you launch it. After you get done, you destroy it. You're done with this. This is the way the CloudBreak works. We have here 3 clusters. These are all 3 different clusters. One has 2 nodes, one has 4 nodes, and one has 4 nodes. It tells you, the first one has 1 master and 1 node. Second one has 1 master and 3 nodes. So it's the third, and one is focused on ETL, the other one in DS, and the other one interactive. Again, you can have as many types of this as you want, and everything gets managed from the same pane. Go ahead. The data in this context is not persisted anywhere, and I'll address the issue of storage. You need to be able to get, either you need to have it on the cloud provider, or you need to get it to the cloud provider. Now, I'll go exactly in that point in a minute. Go ahead.
So where should the Ambari run? Can it run on the cloud and just start up when I want to start the cluster?
Basically, it gets instantiated. When you say deploy a cluster with these parameters, it does a couple of things. It provisions this, it connects to the cloud provider, it creates a VPC, it creates the instances, installs all the cluster software with the stack that you specified. And the stack means I want you to put Ambari version 2.5, I want you to put HDFS version 2.6, I want to put Spark 2.0. Basically, very specific recipes of what you want to put in there. It launches it, and it tells you, I'm ready to go. So it does all those things for you.
And this data cloud should be running somewhere, right?
It can run anywhere. Data cloud is the mechanism to deploy them. Think of it as a single pane of glass for all the cloud providers. So it manages the blueprints for you, it deploys the clusters, it resizes them, it starts them, it pauses them, it destroys them. Here it shows you how you can pick different recipes. Here is specific configurations for the cluster that you can add yourself. You want something specific. You can auto repair. You can also do something which I think is very clever, and we're seeing some of our clients use it, which is spot pricing, which is basically you can, on the fly, bid for computing space with AWS. Typically, it's about 70% cheaper than usual computing space. And then you can run your things that are much, much lower cost. And again, I'll touch on that in a little bit. These are all the components that go in there. Security, operational effort. Basically, it gives you a lot of choices to be able to manage these transparently across multiple things. I'm trying to hurry up here, so I'm running a bit late here. So here I'm going to cover a couple of the things that came up now. So a couple of very practical things. Startup time. I've launched many of these, and typically, for some reason, they tend to take about the same time. It's about 8 minutes, 7.5, 8.5. But typically, it takes 8 minutes for a full deployment. That means connecting to the cloud provider, set up the VPC, provision the servers, install the OS, install the cluster, configure the blueprint, start all services, says I'm ready to process. So it's either really quick or really slow. If you need to have an immediate answer, it doesn't work. You're not going to do this with a web page. You don't want somebody to click the buy button, and you go commission a cluster, and it's going to take 8 minutes before you say yes or no. Once they're up and running, they could be very quickly. But you should always take into consideration that there's an initial time lapse that you're going to be paying to get your cluster up and running. Elastic provisioning, very, very important. Part of the reasons why we're doing this is to make sure that we have an environment that can grow. So we don't want to have the same problems we will have in a multi-tenancy cluster. So you want to make sure that you configure the things to be elastic. You also want to make sure you have multiple cloud providers. Again, you want to be able to optimize your cost. You want to be able to optimize your access. Some of them might be better for some things versus the other ones. And you can always use them as a failover as well. Cluster overhead, another thing that you need to keep into considerations. Cluster, by their very nature, have an overhead. They need to be able to manage these resources. They need to be able to coordinate the nodes. They need to be able to duplicate data. They need to be able to do failover. These things usually make up once you get going because of the parallel access. But you should always take into consideration that there's going to be some overhead that isn't there. And you should always, again, as you design your applications, take that into consideration. Storage, which also came up. Again, there is no storage inherent in deploying a cluster, so you need to get the data there. And it doesn't matter how fast your cluster is running if access to I/O is extremely slow. So you need to figure out how you're going to get the data there, what the timing of it is, and how you're going to manage this. There's a couple of strategies that we've seen that seem to work pretty well depending on the need. First one is called fetch while you wait, which is basically as the cluster is coming up, I have a parallel process which is fetching the data that I need and putting it in a place where the cluster can get to. So in a way, you're parallelizing the readiness of the data while the cluster is coming up. Second one is called storage warming. Due to cost consideration, a lot of the clients that we have are using hot, warm, cold storage. Typically in AWS is attached storage, S3, Glacier. Glacier is really, really cheap, so clients want to keep a lot of stuff in there. But what you need to do as you're going to launch a job, you need to move things from cheap cold storage to hot storage, so that when the cluster is ready to go, the data is there for you to be able to process. Cache loading, specifically for computationally intensive things, very useful, especially Spark. Many times you want to be able to load the cache. You don't want to pay the overhead of going into the disk. So being able to pre-cache things could be very, very helpful there. And finally is what I call stream parallelism. There's a way that you can configure a cluster to maximize the parallel access to the data. In a way, putting a pair of compute and disk together. So if you had 20 CPUs available, you want to have at least 20 disks available. And you want your process to be going at the same time via those 20 CPUs to those 20 disks, so you achieve maximum parallelism. And again, there's things that you need to be aware of, depending on what you want to achieve with your application, to be able to maximize performance. Other things to look at, cluster startup. What's going to be the event that's going to trigger a cluster to be launched? Is it going to be manually every time? Is it going to be event-driven? Time schedule, capacity triggers. You can do all of this with Cloudbreak. It has a REST API. You can actually have a cron job if you want. You can have a cluster startup every day at X amount of time without anybody having to get involved. But again, you need to think about your use cases to figure out what you want to do. Okay, advanced topics. 3 things that keep coming up again: spot pricing, auto-scaling, and obfuscation. Any questions before I get into this? No? Spot pricing. It's actually pretty neat. which is the ability to pay a lot less for on-demand computing. As I mentioned, AWS is 70% cheaper. But there's trade-offs to this. You may not get all the computing power you need. You might be outbid along the way. So the way to do that is you need to be able to overcompensate for this. And we have a couple clients which are doing this. So if they need X amount of capacity, they're going to go for 1.25x of capacity, just in case they might not get everything they need, or just in case they have some wiggle room there. And if you do the numbers real quick, if you're 70% quicker at 1.25, you're still down 62.5%. So you're still paying a lot less for your computing power. First time I ran into this was a financial services client. They have some big jobs over the weekend. They need to run a lot of data crunching routines. And they were basically overbidding for spot pricing. Again, they never had an issue with supply because they overcompensated. And the cost was dramatically cheaper. So this actually works. Questions? These guys are too quiet. Auto scaling. Again, the best way to solve is enabling the cluster to grow based on need. In Cloudbreak, you can do that through either alerts, policies, or general configurations. So this is an alert-based auto scaling. In this case, you're looking at this is a daily access, time-based. So it's doing this every day at 15:10 in the morning. This is a metric-based. This is actually looking at the name node RPC latency. If it reaches critical stage, then it can go over there and make adjustment to the cluster. And this one is an auto-scaling policy. So you have the infrastructure to be able to build in, reactive auto-scaling policies to help you never run out of cluster capacity, which is ultimately what you want to have. The only reason you want to go with dedicated cluster is exactly that. You want to always be able to get maximum fit and maximum power out of your cluster. General. Finally, obfuscation. This is an interesting one, and one that I keep running into in financial services. There's always, because of regulatory reasons, a fear to send the data up to the cloud for processing. One of the solutions that they've done is what they call obfuscating, which is basically before they send the data, they take out any data that could be identifiable to a particular client. They scramble it. They keep the key on premise. They send the data up to be processed. When it gets done, it comes back, and they map it back to the normal state. There's a really easy way to do this, which is Ranger. You can actually set policies to do dynamic masking. In this case, we see two examples here. One of them is obfuscating a social security number, and an identification number. And the other one is basically obfuscating columns that cannot go together. Again, this can be done automatically as you're uploading the data using the Ranger policies. This is more tags. And so recap, Firefly cluster can be launched quickly. They can be pre-configured for a specific task. They can come up, go down, and you can leverage them for expanding your computing power. Questions?
So does this data cloud product has SDK so I can launch as part of my application?
It has what?
Do you have an SDK so like a couple of command lines or?
Yes, it has a REST API. Yeah. So everything you can do through the GUI, you can do through a REST API.
You were picking from specific cluster types, right? Can we provide custom blueprints?
Yeah, of course. That's the whole point, for you to be able to come up with your own blueprints.
When in Hortonworks Data Cloud?
Basically, it's as simple as when you have a cluster up and running, you go down to the configuration and you save as blueprint, and you actually save a snapshot of the cluster that you can duplicate it later. It's really straightforward. And that's the power of this. Go ahead.
How firewall settings and all, do we have any features which can actually, like,
You
white
get,
list a set of...
it gets done through the deployment. What you do is you have to set up the credentials in CloudBreak, and you can find zones. You can do all those things within CloudBreak, which complies to the security of each cloud provider.
So can I have one cluster span from multiple
No, that's still a no-no. The amount of I/O and messaging that's happening within a cluster, it's just not practical for you to have it span multiple data centers.
Yeah, that makes sense.
So you want to have a cluster fully running within
But
one.
it's possible that I have two clusters at different vendors and I want to communicate between them.
You can communicate. You just don't want to have the internals of a cluster synchronizing underneath across multiple data centers. That's something that doesn't work well.
So you mentioned about reading the data ahead while the cluster is being set up. Can you give me like how it can be done? What people do?
It depends where you keep the data. If you keep the data on-prem, you need to be able to get it from where you have it on-prem and start pushing it onto the cloud where it is. If you have it in S3 or in Glacier, you're pulling it out of the Glacier and you're putting it into attached storage. So it's highly depending on where the data is.
Yeah, but then provisioning the server itself, I mean, you do not have the servers to even actually copy from S3 to your local storage.
No, but you can attach an S3 or attach storage after it's loaded. So you can attach it. You can have your cluster up and then attach the storage. We'll do it as part of this while you're pushing this in there.
But that saves only like 1 or 2 minutes. Like if I'm reading from
Maybe.
object storage, it is just...
Depends on the size of the data, yeah. That's highly depending on the size of the data and where the data resides. Any other questions? Yeah, go ahead.
Defining these data sources, is it part of the blueprint too, or do I have?
Blueprints only focus on cluster configuration.
Oh, okay.
The storage piece still needs to be there, and that you need to provide that again because you're the only one who knows where the data is and which data you need to load. So, go ahead.
I was curious whether solutions we discussed earlier, like AWS Lambda or
Yeah.
Google Functions, in effect, would they be doing something similar as an implementation detail when you are really configuring some task to be executed for some purpose and you only need it for short-lived fashion? So where would
They typically have a very specific solution in mind, which is short-lived tasks. And if you look at the SLAs and they look at the limitations they have, everything is same. I'm making sure you come in, you do your thing, and you go. So there's limits on the number of concurrent tasks you have running, the size of the tasks, the data they access. I mean, this is a significant amount of limits on this. Again, because they're optimized to make sure that nothing is holding them up. So they're processing and going, processing and going. Go ahead.
So 2 questions. The first one is, why would I use CloudBreak over HD Cloud? Okay, and the second one is, what strategies would you suggest for dealing with data availability between cloud vendors? So like if you're talking about wanting to do cost management between the 2 cloud vendors, what's your recommendation?
So let me answer the first one. Whether you use a CloudBreak versus HD Cloud depends on the amount of work you want to do. If you're using HD Cloud, everything is nicely packaged for you. All the images are there. Everything is nicely put together for you. But you have to play within the context of what HD Cloud provides to you. With CloudBreak, you get a greater degree of flexibility. And again, if you need to do some things which are a bit more complex, that's the way to go. The infrastructure that HD Cloud uses is exactly CloudBreak. So they're both sharing the same infrastructure. So it's not like you're doing one versus the other one. It's just how much is done ahead of time for you.
So does that mean I can use HD Cloud on like Azure or GCP?
I believe HD Cloud now only works with AWS. I'm not sure if they expanded it yet to Azure, but my understanding, last time I checked at least, it was only working with AWS. Storage is a bit trickier as far as storage savings, because each cloud provider has their own specific offerings. You can always shuffle data from one place to the other one, But storage is one of the things that is highly, highly depending on which cloud provider you're using. Glacier only works in AWS. There isn't an equivalent in Google Cloud, for example, that I'm aware of. And if you look at the cost structure for most firms using the cloud heavily, clearly storage is a much, much higher cost than computing. So they tend to underwrite the computing and make it cheaper, and then tend to get you on the storage side. So they have an incentive to make sure that you're captive to the storage. Anything else? Thanks, guys.
So, one,
Yeah.
in your experience, how much is the latency compared of S3 compared to local storage? Like,
I don't know what the percentage is, but it certainly is lower. If you look at cloud-only, attached storage is very fast, and you can actually get servers which are what they call high-throughput network optimized, which I think is 10 gigabits per second that you can get attached to it. So it's very, very fast. You don't have that option with S3, for example. So it's clearly it's a second tier. It's like warm storage rather than hot storage. Okay.